In this video, we will continue looking at how to use the parallel axis theorem in order to determine the moment of inertia, also known as the second moment area of a section. And so recall that we can use the parallel axis theorem to find the moment of inertia about any arbitrary axis. We can do that with doubly symmetric sections or any arbitrary section. But if we have an unsymmetric section like we have here, that we want to find out what its moment of inertia is about its own centroid, we're forced into using the parallel axis theorem. So that's what we're going to have to do on this example. So we're going to look at a T-section. T-sections are a somewhat common structural form where, you can often they're I-sections which are cut in half. So it's a type of element which we would have to, potentially find out in practice. So in order to do this, the first thing that we need to do is, if we recall that the parallel axis theorem is simply going to be I total is going to be the sum of the moment of inertia of each individual point plus the area of an individual piece plus the distance squared from that centroid of that piece to the centroid of the entire section. So if this is the parallel axis theorem, the thing that we definitely know that we need to find will not only be the little moment of inertia of each piece of interest in the section, the area, again, that's pretty straightforward, but really it's going to be this distance squared between the centroid of a given section and the centroid of the entire section. That's an important aspect. So the first thing we have to do is we have to find what is our moment of inertia, what is our centroid of the entire section. And so we're going to do it from the top, because again, remember, the centroidal distance is somewhat arbitrary. But if we try to find what this y bar is, again, this should be fairly straightforward for anyone who's found centroids before. We can start working out. We'll look at the area of the flange, which is simply going to be 80 millimeters wide times 15 times the centroidal distance here to the top, which is just going to be 15 divided by 2. Equal to 7.5, and we'll add the web area times its centroidal distance to the top here. So 80 times 15 times 7.5 plus 125 times 10 wide times 15 plus 125 divided by 2. 15 plus 25 divided by 2. If we crunch that, that's the same as 77.5. And then we'll divide that by the total area, where it's 80 times 15 plus 125 times 10. And if we crunch the numbers there, we get y bar equals 43.2 millimeters from the top. All right, cool. So now that we have y bar, we can actually start working on determining using the parallel axis theorem and determining the moment of inertia. So we'll do just that. So remember that IXX, if we want to go about the x-axis here, is simply going to be the sum of each little piece, its moment of inertia about its own centroidal axis, plus its area multiplied by the distance of its centroid to the centroid of the entire section, and that value squared. So what we'll do is we'll write it out in sort of terms of what each piece is going to be. We'll draw it pictorially, and then we can crunch the numbers, just so that we're really clear given that this is one of the first examples that we're doing using the parallel axis theorem. So if we sum this up, really we want to break this into two convenient pieces. So one convenient piece would be the flange, and the other convenient piece would be the web. So if we follow through in the parallel axis theorem, we would have it's going to equal the moment of inertia of the flange about its own centroidal axis plus the area of the flange multiplied by d flange squared. And then we would also look at the moment of inertia of the web plus the area of the web multiplied by the distance of the web squared. So let's draw this pictorially first. And as I said, we effectively are just going to break this out into each piece. So what I'll do is I'll just draw each of these components as a picture so that it's just really super clear how we're working this out. So we'll work on the flange here. And then, of course, we got the web coming down plus the contribution from the web. So with the flange, it's going to have its own centroid, and it'll have a moment of inertia, I, x, of the flange. So the moment of inertia of this little rectangle about its own centroidal axis. Obviously, there's the centroid of the entire section, which is down here at y bar. Our distance d flange is just going to be the distance between the centroid of the flange and the centroid of the entire section. So df is simply going to be y bar minus effectively 15 minus 2 minus 7.5, right? Just the distance between these two, and then we have, of course, the area of the flange. So that's each of those pieces, and we know how to calculate each of those. We know how to calculate the moment of inertia of a rectangle. We know how to calculate the area of a rectangle, and we can work out what the distance between the centroid of the flange to the centroid of the whole section is. Similarly, too, for the web, again, it's going to have some y bar. We'll just make sure that we make this plus sign nice and apparent. There'll be some centroid of the web. It'll have some moment of inertia about this axis. There'll be some distance d, and it's that distance between the centroid of the entire section and the centroid of just the web itself. And of course we have the area of the web. So that's pictorially what we're doing. That's just really breaking down what this equation is saying. So now let's put some numbers to it. And we would have our moment of inertia about the centroidal axis and the about the x direction there is simply going to be 1 over 12 times 80 times 15 cubed, 80 wide, 15 high, plus 80 times 15 times 43.2 minus 7.5, that quantity squared. And again, we'll just write out, this is I the flange. This is the area of the flange. And this is D of the flange. And again, this is all just shown pictorially up above here. To that, we'll add the contribution of the web plus 1 over 12 times 10 times 125 cubed. Web is 10 millimeters thick, 125 tall, plus 10 times 125 multiplied by 77.5 minus 43.2 squared. And so the 77.5 is simply, the location of the centroid of the web relative to the top minus the y-bar relative to the top. So that's just half of the web plus the flange minus 43.2 being y-bar. And again, we'll just write out, this is I web, the area of the web, and this is D web. All right, if we're to crunch those numbers, we would get IXX equals 22,500 plus 1.53 times 10 to the 6th plus 1.63 times 10 to the 6th plus 1.47 times 10 to the 6th. So this is all just effectively arithmetic, but an important thing to note here in terms of relative contribution of each of these pieces. So if we look at the component from the flange, we see that the moment of inertia of just the flange itself is pretty small, which makes sense. It doesn't have much depth. It doesn't have much distance of material. It doesn't have much material which is far away from its own centroid. So we would expect it to be small. However, the contribution of this area getting rotated about this axis is pretty significant. It's almost as big as just simply the rectangle of the web rotating about its own centroidal axis. And it has an even bigger component than this whole bit of the web rotating about the centroid of the entire section, which should make sense because this D, the distance between this centroid and that one, is smaller. So if we think about this as, analogous to moments, if we think of effectively the area is analogous to load, and then, your distance from your axis of interest is like your lever arm, we can increase a moment by two ways. We can either increase its distance or we can increase the load. Similar here, moment of inertia, we can either increase the amount of area or its distance away in order to increase our moment of inertia. So just a thing to note that, this is really, it's this bit spinning around the centroid is where a lot of this contribution is coming from. So if we're to work this, sort of plug all of this together, we get to our final answer. IXX equals 4.65 times 10 to the 6th millimeters to the 4th. So that's it in a nutshell. That's how you determine the moment of inertia of a T-section using the parallel axis theorem. So again, drawing everything out in kind of small pictures. Hopefully this was helpful in illuminating where each and every piece comes from. The big thing to remember, though, is that you always got to account for effectively the macro portion of the second moment area. If this is sort of the micro portion of the component itself spinning about its own centroid, it's taking this whole area around the axis of interest that we care about. So that's how we determine the moment of inertia about a given point using the parallel axis theorem of a T-section. So with that, thanks for watching.